How does a cross-trainer get your heart pumping and your legs burning? What allows a turnstile to let workers through but stop intruders in their tracks? How does a 3D printer create perfect replicas of the most intricate objects? To answer these mysteries, we dive deep inside these and other extraordinary machines to reveal the secrets of how things work. The cross trainer, an essential fitness machine and staple of gyms across the world. How does this machine give us a workout like no other that gets our hearts pumping and our legs burning? It's a treadmill and bike rolled into one. Iron cranks and flywheels turn walking into cycling. A powerful generator controls resistance and powers the machine. Perfectly balanced polyurethane wheels give a super smooth ride. On the handles, electrodes can sense the heartbeat in your sweaty palms, so you always know how hard you're working. The cross trainer is built to last for 60 million steps over its lifetime. The secret to its longevity is how workers assemble its steel frame in this Washington factory. Workers here designed and built the first cross trainer back in 1995.
This machine does have to be pretty strong. There will be people run on this thing probably 24 hours a day sometimes.
Brad builds cross trainer bodies that the world's strongest man would be proud of.
Here's the main structure of the whole machine. I tap on these clamps just to make sure everything's locked in position.
This robot welds the entire frame in under 3 minutes. Task complete. Brad carefully checks the welds to make sure the frame is fit for training. The joint in the middle of the frame is the most vulnerable.
This is where most of the force is applied. Instead of one continuous weld, we have separate welds. Just in case one weld does fail, there's multiple to hold it on there.
With the frame complete, the team's next task is to build and attach the pedals. Whether you're a beginner or a 100-kilo powerhouse, the pedals on a cross trainer are the key to pushing your personal best. This machine makes sure that no two workouts are the same. Every step you take revs up the cross trainer's electric power system. 2 supersized bike pedals spin 2 pulley wheels that boost the speed. They drive a generator that provides resistance. When you're at the toughest setting, you can generate enough power to run a washing machine. The circular movement of the cross trainer pedals allows you to run without your feet ever hitting the ground. This low-impact running motion is great for your knees, but it creates a problem for the machine. The metal rod connected to the pedals, called a stair arm, must move millimeters side to side with every rotation. The movements are tiny, too small to see, but over the machine's lifetime, they are enough to destroy the bearing. Feynman engineers the solution: a flexible connection.
The steer arm needs a pivot block because you need that flexibility for that smoother ride.
Feynman presses a pin through the pivot block to join it to the stair arm.
They still have that flexibility of moving side to side as you're riding it.
With arms that will wear out long after you do, this machine can keep up with the fittest gym goer. To get really fit, you need to run on an incline. How does the cross trainer make you feel like you are slogging it to the top of a mountain? Right under your nose, beneath the front cover, sits a small electric motor. This drives a set of gears. The gears slowly turn a steel spiral that jacks up the trainer's ramp. The incline makes you feel like you're running up Everest. For the cross trainer to deliver such a tough workout, it has to be free of dirt and grime. Any lumps and bumps in the system could ruin a good sprint. The only way to ensure a cross trainer is running smoothly is to take it for a spin.
Since everything looks good and secure, I'm just gonna hop on the unit and ride it.
Every machine made on the production line comes through the test booth.
I'm bringing the ramp down while I'm doing it, and then pushing the resistance up to 20. And it's pretty rough, and it's there, you know? So you can get a good feel of it. This one feels great. The ride is smooth, so now I just gotta have to ship it out.
Finely tuned by the human ear and strong enough to dish out the toughest training regimes, the cross trainer is the gym kit that won't let you rest. The 3D printer, a micro factory that fits on your desk. This machine lays down thin layers of molten plastic, one on top of the other, to create almost any 3D object you can imagine. How does the printer control this jet of liquid plastic with microscopic accuracy? Three robotic arms give the printer pinpoint precision and lightning speed. A print head squirts out melted plastic. Down below, a heated glass base holds the new product in place. Underneath, three motors drive the machine. They move in tiny steps, smaller than a hair's breadth. These elements work together to print the perfect 3D shape every time. To print successfully, the machine must turn solid plastic to liquid in less than 2 seconds. In this Indiana factory, workers have the key to this turbocharged melting power. The electrical component that controls the flow of melted plastic is called the hot end.
The hot end is the most important part of the printer. If you're not melting plastic, you can't print.
Andy puts the hot end together.
The plastic comes in through the top, and then it has our melt chamber down here. What we don't want is to melt the plastic too early, which is melting anywhere above the heating block. If the plastic is melted too early, it'll expand and block up your hot end.
Andy must assemble each hot end from 10 components. The key part is a beige thermal shield that stops the heat from spreading too far up the hot end.
The middle section is a substance called PEEK. It holds high temperatures so it can withstand the heat, but it doesn't transfer that heat to the filament so it won't melt your plastic early.
Andy uses heat-resistant silicon glue to secure 2 heating elements inside. They convert electrical current to heat and get the hot end hot enough to melt the plastic. For intricate designs, the machine can print a new object every 2 hours. To keep up this pace, the hot end needs to be fed with a continuous stream of plastic filament. This is how the machine does it. At the back of the printer, an electric motor pushes the filament up towards the print head. Non-stick tubing ensures the plastic doesn't snag as it enters the hot end. As the plastic melts inside, it expands and shoots out as a jet thinner than a cotton thread. The robotic arms then lay this down in any shape you can dream of. The 3 robotic arms must be exactly the same length. This is the only way the machine can position the hot end accurately enough to print intricate shapes. The key to getting the arms the right length is down to the way Mark makes them.
The arms start out as little beads of plastic. From then on, it goes through the molding process.
Mark Fulk creates the limbs of the printer. He carefully mixes the plastic for each batch.
To get an accurate print, they have to be the same dimension all the way around. That's where we use the injection molding machine to make them the same over and over and over.
The finished arms need to be perfect, or Mark will have to trash hundreds of useless parts.
When these 2 mold halves come together, it will leave a void in there, and we fill the void with plastic.
The mold is made of aluminium. This soft metal is easy to cut into shape, but tough enough to withstand the scorching molten plastic.
We're ready to start.
Mark heats the machine to 250 degrees, hot enough to liquefy the plastic. A hydraulic ram pressurizes the liquid and squirts it into the mold. Seconds later, it's set hard.
There you go. There's the finished part. And they always come out exactly the same.
The printer's arms move the hot end in steps of only a 50th of a millimeter. What gives these plastic limbs the precision of a heart surgeon? Tucked away under the glass bed, a circuit board stores the print data. It runs high-precision motors that turn in tiny steps. The motors drive a toothed timing belt that runs through aluminium columns. The belt controls a carriage gliding on smooth rollers. The carriage moves both the arms and the hot end with microscopic accuracy. Each layer laid down by the printer must sit perfectly on top of the one below. If it doesn't, the finished item will be the wrong shape. This is only possible if the object being printed doesn't slide around on the bed.
Failure is always an option when printing. If the part comes off the bed, it's going to move around and there's no recovery. You'll end up with spaghetti coming out of the nozzle. To keep the part in place, we have a heated bed. That heated bed helps keep the plastic tacky enough to stay in place on the glass and not to peel off or come loose.
With the bottom of the object stuck down, the print can be made without snarl-ups. Dexterous, fast, and even capable of making its own body parts, the 3D printer is the ultimate workshop companion. The food mixer, a mechanical baker that no professional kitchen could do without. How is this machine capable of churning through a bowl full of thick dough? Beneath its skin sits a powerful motor. It can wrestle dough for hours and not burn out. A gearbox amplifies the kneading force. Down below, it has a tough aluminium mixing hook that won't bend or break. 86 kilos of metal muscle that never gets tired. Plowing through thick bread mix is the food mixer's hardest task. The way it is built in this Ohio factory is the key to how it copes when the doughing gets tough. Workers here manufactured the world's first mixer in 1914. On its own, the mixer's electric motor is not enough to tackle the thickest mix.
It would be extremely hard to mix with just a motor sitting here. It takes all the gears combined together to mix the thick dough.
Brandon gears up the machine for the task.
This machine has a gearbox, sort of like a car.
Brandon installs 9 cogs that reduce the speed from the motor but increase its strength. He must fill the gearbox with grease to lubricate the gears, but the grease creates a problem.
You need the grease to stay in the gearbox and not down in your food.
Brandon bolts down this top plate to seal the gearbox. He must tighten the bolts carefully or the gears could be ruined.
If you don't put the bolts in properly, it could cause this whole top plate to be lopsided, which can break the teeth on the individual gears. After the top cover is locked down, I turn this to make sure none of the gears are binding and everything moves freely. It looks good.
For a good bake, it's critical to get an even mix of ingredients. Just stirring the mixture from the center won't blend everything properly. But how does the machine make sure no piece of dough gets left behind? Under the mixer's hood, a half-horsepower electric motor rapidly spins a drive shaft. The gears slow the revs but crank up the force. Under the gearbox, a small cog spins as it moves around the inside of a larger gear wheel. The gear wheel turns the hook, which scrapes the dough from the edge of the bowl and pounds it in the middle. Before it leaves the factory, the team must test mix a batch of dough. Teresa is the testing lab's head baker. She uses a robotic dough mix known as a brake instead of flour and water.
This is a brake, and it simulates me using a bowl with a beater to mix up some dough.
The brake fits directly onto the machine's rotor. It uses air brakes to mimic the force required to mix a bowl full of ingredients.
This test lets me know that this mixer is capable of the customer being able to use it and mix dough.
Teresa's ears are finely tuned to the sound of anything out of the ordinary.
If there is a burr on your ear, you're going to hear it thumping. Or the speed, sometimes the speeds will jump. This one sounds good and is ready to be cleaned and shipped to a customer.
This mixer is finally ready to start its life as the workhorse of the kitchen. Without a food mixer, making bread is more work than play. Thanks to this ingenious invention, you can take the backache out of baking. The frozen yogurt machine, dispensing delicious chilled treats. How does it convert liters of liquid yogurt into fresh, fluffy, frozen dessert? Stainless steel tanks hold 230 portions of yogurt. It flows out of the bottom through a valve that injects air to make it light and fluffy. Seamless steel cylinders freeze the yogurt in just 8 minutes. A churning blade keeps the product soft and creamy. And at the front, a mixing tap adds a little twist. The freezing cylinders hidden inside must be hygienic and bacteria-free to make sure that the machine dispenses dessert that tastes fresh. But how do you keep something clean when it's constantly covered in frozen yogurt? The key to this lies in how workers make the cylinders in this Wisconsin factory. This company helped invent the first frozen dessert dispenser in 1939. Workers make the cylinders out of a single flat disc of metal with no joins or seams to make sure they're easy to clean.
We want to end up with that right there. What I'm holding here is the finished tube, which is used in the yogurt machine. And it's nice and smooth.
Bruce must create a cylinder that is flawless. He uses a hydraulic press to apply the equivalent weight of a grizzly bear to force the flat sheet into a cylindrical shape. But he can only go so far. To make a long, thin cylinder in one go is impossible. The metal would crack and split. So it has to be done in 6 stages. Before each stage, Bruce must heat treat the metal to give it maximum flexibility. He puts the cylinders through a huge conveyor oven. It heats them to the temperature of lava and then rapidly cools them. Bruce can now press them again. Each press squeezes them longer and thinner. Five presses later, the cylinders are finished. But that's not the end of their story. In the completed machine, the cylinders get so cold that the yogurt inside them could easily turn to a hard block of ice. Not good for the customer who wants fluffy and light froyo ready at the pull of a lever. This is how the machine keeps the yogurt frozen but flowing. Copper pipe full of coolant wraps around the cylinders. Inside them runs a shaft with 4 curved paddles that churn through the freezing mass. Powerful springs push the paddles outwards. They scrape the freezing yogurt off the cylinder before it sets hard, keeping it moving and ready to serve. It takes an intricate cooling system to get the temperature below freezing. After the cylinders have been pressed, workers coat them in resin. This makes sure that the copper pipes stick to them tightly. These pipes are the arteries of the machine. They channel the refrigerant, a freezing fluid that chills the yogurt down. Jennifer's job is to bring this machine to life.
Connecting the refrigeration lines is the most critical part of the job. Making sure that there are no refrigerant leaks is key to a successful frozen yogurt machine.
Jennifer fills the machine with a safe gas, helium, before she adds the refrigerant. This helps her check the quality of the joins.
We double and triple check our work here to make sure that there are no possible refrigeration leaks.
She uses a highly sensitive helium detector to sniff out any escaping gas.
The test's going great. We haven't heard a single peep, so there are absolutely no leaks.
The cooling system can turn liquid yogurt to frozen dessert in less than 10 minutes. But as the yogurt starts to freeze, it gets thicker and harder to serve. So what stops this machine from grinding to a halt? As the mixture freezes in the cylinder, it starts to slow down the paddle. But the machine has an onboard computer that can sense the tiniest change in speed. The computer shuts off the refrigeration and stops the yogurt freezing, allowing the motors to get back up to normal speed. This keeps the froyo at just the right consistency. Even on a busy day, there will be gaps between customers, and this creates another problem. Any froyo stuck in the nozzle will slowly start to melt. This will give the next customer a sloppy serving.
As soon as the frozen yogurt leaves the machine, it starts melting.
Kelly makes sure that only completely frozen yogurt greets the customer. She assembles plastic stoppers into a door and fits them directly to the front of the machine. The stoppers hold back the yogurt until the customer pulls the handle. When the serving is complete, the stopper or spigot drops back down. It cuts off the flow and pushes out all of the remaining yogurt.
When the customer releases the handle, the spigot will push all of the product through the door, and there will be no melted product sitting in the door.
No matter how long the machine waits between customers, it's always ready with the freshest froyo. The frozen yogurt maker, a turbocharged freezing machine standing by to refresh the hottest customer. The turnstile, a mechanical sentry that never gets tired and never makes a mistake. How does it stop unwanted visitors in their tracks, but allow guests and employees through? 33 highly polished steel arms block the way. Inside a weatherproof box, a digital brain knows who's allowed in. Magnetic motors control the gate. Located under a massive drive wheel, mighty steel ratchets stop illegal entry. And a hydraulic shock absorber soaks up the bumps to give this metal bouncer a gentle touch. Engineering the turnstile is a challenge. How do you make it light enough to push round, yet strong enough to keep intruders out? The secret lies in how workers construct the gate at this North Carolina factory. It's crucial that they select the right materials.
316 steel is one of the best stainless steels you can use on a turnstile. It's very lightweight and it's weatherproof. Rain, snow, sleet, it doesn't matter, it still comes out with a perfect finish.
Mike makes the arms for the turnstile gate. He cuts each arm to length. But this leaves the metal jagged and sharp, painful for anyone brushing up against it. The solution? He melts the pipe to seal it with a smooth, round finish.
I heat it up till it's real hot, then I form the end.
The blowtorch shoots out flammable gas and high-pressure oxygen to create a flame 20 times hotter than your kitchen oven. The end result is an arm with no sharp edges and no weak spots.
Tougher than my car, tougher than nails. Solid, but it's still at the same time as lightweight. Very lightweight.
Once cooled, Mike polishes the arms to provide the perfect finish. The arms stand firm in the path of trespassers. But how does the turnstile transform them from impassable barrier to open door at the swipe of a card? At the top, two thick steel ratchets block unwanted visitors. When access is granted, a magnetic motor pulls back the locking bar to open the gate. Every entry trips a contact switch. This makes the magnetic motors drop the bar back in to relock the gate. Workers in this North Carolina factory construct the ratchet from 19mm steel to keep out the most determined intruder. It takes serious manufacturing muscle to cut metal this thick. Workers cut the ratchet wheels from a sheet of metal bigger than a king-size bed. It weighs more than a small car. It's nearly impossible to cut these intricate shapes with a saw.
Well, I wouldn't want to have to do it, I'll tell you that, but it probably would take 2 or 3 hours just to do one ratchet by hand, if not longer.
Laser operator Kenneth harnesses the power of this 4,000-watt cutting tool. The laser focuses a beam of infrared light onto a single point the width of a grain of sand. The metal under this point melts instantly. High-pressure gas blasts it away.
It cuts exactly what we want every time. Exactly what we want.
The ratchets are ready to guard the turnstile. The correct access unlocks the ratchets and a push gets the gate spinning. 100 kilos of metal are now on the move. If they spin too fast and hit you, it's going to hurt. How does the turnstile keep you safe as you rotate through this heavyweight stack of steel? The revolving gates turn a gear the size of a dinner plate. This drives a smaller cog which pushes on the arm of a shock absorber. Inside it, oil squeezes past steel balls to slow down the revolving gate. This way, when you give the gate a shove, it doesn't hit back. The Turnstyle's onboard computer knows when to grant access and when to hold firm. But what if the electricity fails? Could a power cut trap people inside?
Well, in an emergency situation, obviously you want people to leave.
Travis makes sure the Turnstyle won't block people who need to exit in a hurry. The solution is a simple spring. The spring fits onto the exit ratchet lever. With the power on, the system holds the lever closed and keeps the exit locked. But if the power fails, the system releases the lever and the spring flips it open to allow people through.
Power to the building, cannot leave unless you card out. Power cut, you can leave. So it functions correctly.
This ingenious mechanism gives the gate a fail-safe, so no one gets stuck.
This one's perfect. Perfect. Perfect working unit. Ready to go.
Always on guard, whatever the weather, it doesn't take breaks and never sleeps. The Turnstyle, it is the ultimate doorman. The ubiquitous office chair. We sit on one of these for up to 8 hours a day. A badly designed seat can lead to hours of misery. So how does this machine keep the world's workforce comfortable? 100 parts work together to keep you comfy. At the back is a spine made of glass-filled nylon. Underneath, plastic leaf springs give a smooth and balanced recline. A pressurized gas spring allows flexible height adjustment. At the base, wheels that lock the chair in place when you get up. And a seat that can take the weight of a baby elephant for 100,000 hours. For this chair to keep our backs in good health, it must support them from bottom to top. But this isn't easy when we're constantly shifting in our seats. The team at this factory in Wiltshire knows the secret to building a chair that offers total support to our spines.
A perfect chair will flex with you as you move.
The chair's unique tilt mechanism is the key to this seat's flexibility. Josh starts each chair assembling this system by hand.
The tilt mechanism is the heart of the chair because it holds all the controls. Without the controls, there would be no adjustment. And you need a chair that's fully adjustable, so it's suitable for all people.
18 components make up the chair's tilt mechanism. 2 are absolutely crucial to a healthy back.
New bits are the leaf springs, which allow the back of the chair to flex with the desired movement of the person.
The springs hold the backrest against our spine and let it move as we move.
Because this allows the chair to flex, it will mean that the person will always be supported on the back of the chair.
This central mechanism forms the heart of the chair. But a chair will still be uncomfortable if it isn't at the right level for the length of your legs. How does the office chair allow each of us to adjust the seat to the perfect height? The secret is the gas lift. It's a cylinder full of nitrogen at 30 times the pressure of a car tire. A lever under the seat pushes a button on the gas lift. This opens a valve that allows the gas to flow out of the cylinder. So you can either drop the seat or use the pressure inside to raise it. It is both shock absorber and elevator. Office chairs take a beating over their lifetime. Once built, Chris Owen tests the chairs to ensure they can withstand years of being squashed underneath us.
This chair is designed to last for 12 years, continuous use. I'm loading the chair with a representative weight. So this is a 102 kilogram person sitting on the chair.
It's just the start of what Chris has in store for this poor seat.
This is a pneumatic ram, and so I can adjust the amount of force that's exerted on the chair by the pad. This test is designed to simulate somebody leaning back hard on the chair 10 times an hour, 24 hours a day, 365 days a year for 12 years.
The test will run day and night for 6 weeks.
If something does happen overnight or over the weekend, then I can just come back, check the footage on the cameras and see exactly when it went wrong and what happened, the mode of failure.
This chair is designed to offer complete back support and built to withstand non-stop use. The average office worker will spend more than 2.5 months each year sitting at their desk. That's a lot of uncomfortable shifts without the supporting embrace of the perfectly designed office chair. The cross trainer, the mighty food mixer, the frozen yogurt maker, and the turnstile. What's inside isn't always big, but it is clever. Next time you see one of these machines, remember, there's more to how things work than meets the eye.